For this video, we are going to start talking about group and why do we discuss this in terms of abstract algebra. Now, in abstract algebra, a group or its purpose is actually to generalize and unify mathematical systems that probably behave in the same way under the same operation. Because for a group to be considered to be a group, we use here the idea of a binary operation on the same set and together with its conditions. This allow us to study a certain set altogether and apply the results broadly. Actually, groups do connect or unify some concepts in mathematics, like in number theory. We also have it in geometry, and of course abstract algebra and linear algebra. So how do we define a group? Okay, and what is a group, or when can we say that a certain set, yes, it's still a set, when can we say that a certain set is a group? So here is its more formal definition. A group, okay, let's say here G and star. We're using now G, but since it's still a set, okay, is a set G, okay, closed under the binary operation star such that the following conditions, here are now the conditions or criteria or actions, are satisfied. Okay? And the first one, G1. Okay? You will have here, for all A and B, C element of G, we have, okay, A star B star C is just equal to A star B star C. This is actually the associativity, as this previously discussed, of your binary operation star. So that's the first condition. Actually, it could be considered as the second condition, because you could say that the first condition is that the operation is actually a binary operation, or in short, again, closed. Okay? That's why you can consider associativity as the second condition if you are going to consider binary or closure property as your first condition. But nevertheless, for its formal definition, G1 means associativity is satisfied. Okay? If G1 is already not satisfied, then a certain set G is not a group under the binary operation star. Let's talk about G2. Okay? So G2, the second condition, there exists E in G, okay, or element. Okay? There exists E as element of G such that for all, let's say, X element of G, we have here E star X is equal to X star E still equal to X. This is the existence of the identity element. This is why we discussed first the idea of identity element before talking about what is the group. So identity element for your star. Okay? So aside from associativity being satisfied, there should exist, as we know that it also in the uniqueness theorem, we know that identity element may also not exist for a certain set and using the operation, but this time, for it to be a group, aside from associativity and of course closure property on the binary operation, the existence of identity element is noted. And finally, for our third one, we only have three conditions if you're going to consider closure as the first idea but not necessarily one of the actions. So you have here, for every use here, for every X element of G, right? Or any value, you may use A or any value here. Now there exists element, okay, let's say X prime still in G, such that if you're going to operate X with the given X prime, right, it's just equal to X prime star X is equal to your identity element. Okay, so the G sub G1 is associativity of star, G2 is the existence of identity element for star, and what is G3? This tells us that there exists, okay, the inverse element of X, okay, in the same set. Meaning, if we could guarantee that the identity element is existing by G2, and we can establish that for every X there exists another element of the same set that when operated will result to your what they call this one, your identity, or even in this manner, that certain element to be operated with X will still return to your identity element. These are actually inverses or existence of inverse element. So with this, we can say that X prime is the inverse element of X, and at the same time X is the inverse element, okay, of your X prime, because when they are operated with using the binary operation star, they actually results to the identity element. So this will be further illustrated by some examples later on, but basically for a certain set to be a group, okay, it should satisfy these three axioms together with the assumption that the star is already closed, or the star is closed in the same set G. And then G sub 1 associativity, G sub 2 existence of identity element, and G sub 3 existence of inverse element for every element in G. Take note here, I would like to emphasize that our identity element is for all x's in G, but our inverse element, there exists a specific or a unique inverse element for every x in G. And if these three axioms are satisfied as mentioned, then we can establish a group, the set to be a group. Again, we will have illustrations for this as we move forward through this playlist. Thank you very much for watching.